Good afternoon, everyone. I'm Vaishalee, working as a research engineer in Center for Study of Science, Technology and Policy, Bangalore. Today I'll talk on the topic Technical Assessment of Thin-Film Solar Cells. And it will be good if you can keep all your questions till the end of the session, that is after I finish presenting all the slides. And then we can take up each of the questions one by one. So coming to the outline of the presentation, we will go through the introduction, the technology overview, the device structure, the best fabricated cells for the three technologies that I'm going to discuss today, efficiency and process correlation, qualitative and technical comparison of the technology, the historical efficiency trends and the material requirements, and finally we'll come to the conclusions. Just give me a moment. So coming to the introduction for the presentation, first we go through why we do this work, because we see that the current thin-film industry, the PV industry especially, face certain challenges such as tough competition from silicon-based PV industry. That is, silicon-based PV is a very established technology, so thin-films have to be that good enough to compete with such an industry. Then we have low efficiencies of these thin-films existing today. The PV cells have very low efficiencies compared to their silicon counterparts, and the high manufacturing and production costs involved currently in thin-films is one of the major challenges involved. And so most of these thin-films today are using rare materials, and like the indium and tellurium, and also some of them are toxic, like the cadmium is used as a buffer layer in both CIGS as well as CSTEP. And the degradation that is involved because of environmental impacts, that is also again one of the major challenges faced by the thin-film industry today. So in one line we can say that we have to look for options beyond the silicon-based PV cells. That is one of the major motivations for carrying out the study. So coming to the overview of this technology, what is CSTEP? We chose three particular technologies, that is CSTEP, CIGS and Perovskite based dye-sensitized solar cells. So CSTEP basically means copper, zinc, tin, sulfide cells, where the constant elements are copper, zinc, tin and sulfur, as I mentioned, which are all abundantly available in non-toxic materials. And best part is that they can be manufactured on cheap, flexible substrates. But one problem that they face is that is low efficiency. Today these cells are quite less efficient compared to their counterparts. Whereas on the other hand, we have CIGS solar cells, that is, which stands for copper, indium, gallium, selenide solar cells, which currently have the highest efficiency among all other thin-film solar cells that are existing. They have good outdoor stability, and they also can be produced at a very lower cost. But the only problem with that is just that indium availability is very low. The Earth doesn't have that much reserves of indium. So in future, there might be a problem because of this indium availability. Now coming to the perovskite-based dye-sensitized solar cells, it's basically the material is called methyl ammonium lead halide. It can be a lead iodide or a lead bromide basically. And this is one of the layers which is used in dye-sensitized solar cells for absorbing more photons from the sunlight. And within a few years, we have seen that efficiency of these perovskites have gone by leaps and bounds, and they have reached very high levels of efficiency, almost comparable to multicrystalline solar cells. That is why there is a lot of focus on perovskite-based dye-sensitized solar cells. As I was talking about the availability of elements, constant elements, we can see that CSTEP, that is copper, zinc, tin. Here we see that copper and zinc occupy quite high positions in the abundance chart compared to, if you say, indium, which lies somewhere down the chart. It is not exactly a rare element, but it is quite close to the rare element group. And in that sense, we see that CIGS is a technology where indium availability might cause a problem later on. So coming to the device structures, so these are the block diagrams that we've made to compare the three device structures. Basically, CSTEP and CIGS have very similar device structure. There we see that there is a glass layer at the bottom, and it has a molybdenum-based substrate on top of it. And then we have either the CZTS or the CIGS layer, and it has a buffer layer that is CDS, called CDS, and a ZNO coating, and finally the transparent conducting oxide. So molybdenum basically acts as a substrate which against the harsh conditions that the module might be exposed to. CZTS or the CIGS, they are actually the P layers of the device, and the CDS is the N layer. This is required to form the PN junction basically. And the CDS layer actually is, the ZNO layer actually acts as a coating on the CDS because the CDS might not fully cover the junction. So in order to prevent short circuit, the ZNO layer is given, and the top conducting oxide is basically for the encapsulation purpose. Similarly, for perovskite based dye sensor, it is slightly different from the other technologies, but we have a glass layer for protection, and then we have a anode, that is the FTO, fluorine doped tin oxide. And TiO2 and hybrid perovskite layer form the sensitizer, which basically to absorb more photons from the sunlight. Then we have the electrolyte, that is the HTM layer, is the electrolyte that is used. And finally, the AU is the gold layer, the layer of gold that is deposited to form as the cathode. Now, so the study basically began with looking at the fabrication scheme, so the ways in which, or the processes or methods in which these solar cells are fabricated. So basically, the two charts, first chart shows the synthesis of classification of fabrication scheme used for synthesis of CZTs or CIGs. Basically, there are two types, either vacuum-based or non-vacuum based, and the different processes are mentioned below. And similarly, for perovskites also, it's basically non-vacuum and vacuum, and the processes are mentioned here. So we did analyze each of the process and tried to see by which process how much efficiency solar cells, or what was the efficiency of the solar cells produced, and then classified all these data and found out the best fabricated solar cells for each of the three technologies, that is either CZTA, CIGS or perovskite. So in this chart you can in this table you can see actually that the CZTA solar cells, basically the first three, the purple colored, the data shows vacuum-based processes, and the red ones show the non-vacuum process. Here we can see that clearly that the non-vacuum processes lead to better efficiencies. That is, you can see at the end 12.6% efficiency is obtained by a hydrazine-based process, and that is mostly because this so the non-vacuum processes lead to better efficiencies because their material absorption is better, and it leads to better absorption on the layer of the substrate. And we see that here in this case for CZTA solar cells, fill factors and efficiencies are not as high as compared to the multicrystalline solar cells. It's just about 12%, whereas there the efficiency is near about 20%. So compared to, so coming to what is efficiency and fill factor, especially fill factor if you want to see, then fill factor is basically the ratio between the IMP and VMP, which is the maximum current into maximum voltage produced by a solar cell, divided with the short circuit current and the short circuit voltage. So it represents the squareness of this IV curve. Here the pink line is the IV curve of the solar cell. So it is basically showing how much maximum power can be extracted out of the solar cell. So if IMP and VMP are same as ISC and VOC, it will be like 1. Which is never possible because IMP and VMP cannot be same as ISC and VOC. Now coming to the best fabricated CIGS cells, here we see a different phenomena, that is the highest efficient cells are obtained by in a vacuum based process basically. That is, we can see here 20.3 is the efficiency from a thermal co-evaporation process, and fill factors are better compared to the previous case because here the open circuit voltage, the short circuit current is very high in CIGS solar cells compared to the CZTA solar cells. And in each of the cases, we have also mentioned the materials or the precursors that we use, that is the source materials used. And coming to the perovskite cells, here the efficiencies are as good as in both vacuum as well as non-vacuum processes. Like you can see 15.4 and 15 are obtained and if you follow the vacuum or the non-vacuum process. And here one of the advantages of getting high efficiencies, or you can see one of the reasons for getting high efficiency is because of a very high open circuit voltage. I mean, the open circuit voltage here is much higher compared to the previous two cases. So basically, what we conclude out of the three is that one of the factors is that for getting higher efficiencies for each of the three technologies, first the CSTEP is getting better efficiency using a non-vacuum process, whereas in CIGS, through a vacuum-based process, we get better efficiency. However, in perovskite, both vacuum as well as non-vacuum processes lead to higher efficiencies. Now, coming to a qualitative comparison of the three technologies, we see that coming to the pros and cons of each of them. So in CSTEP, they are all non-toxic abundant materials which are used. They have high absorption coefficient, a very optimal band gap for better absorption of light. Whereas on the other hand, the efficiencies that are achieved till date are very low, that is somewhere around 12% as compared to the counterpart silicon-based cells, or even for the other matter compared to cells like CIGS and perovskite also, it is low. And the use of cadmium in the buffer layer is the problem because cadmium is toxic in nature. But in CIGS, the pros are that the efficiency is comparable to silicon-based solar cells, that is around 21%. It has excellent stability also and very high absorption coefficient and a high charge carrier mobility as well. But the disadvantage is that indium availability is a big issue. The Earth does not have enough resource of indium. And again, the toxicity of cadmium is also an issue here. And coming to the perovskite, the pros are that we have very high lab scale efficiencies, around 18%, and excellent charge carrier mobility, ambipolar properties, because that same layer can act as a layer to transport both holes as well as electrons. And it has the potential also of low cost fabrication. But the disadvantage is that lead, which is used here, is a toxic material. Lead is used actually in the perovskite layer, and that is a toxic material and which causes a problem. And also its water soluble property is good for chemical synthesis, but it reduces device stability. Now coming to the technology comparison, so we see that for availability of materials, we see that source materials in case of CSTEP are abundantly available, whereas in CIGS there is a problem with indium and selenium availability. And also, but for perovskite there is no such material availability problem. In case of CIGS, gallium production is expensive, and in perovskite we see that the electrolyte layer, that is the HTM layer used, those are expensive materials. Coming to toxicity, cadmium toxicity is a concern for both CSTEP and CIGS. In case of perovskite, the lead is a problem. With alternative tin is also under research, but it's a slightly unstable material. There's more research going on in that particular direction as to how to make tin, the use of tin as a layer in perovskite. And coming to structure-wise, these three have three different structures, that is chalcopyrite, chalcopyrite, and perovskite structure. Coming to the fabrication route, we see that in CSTEP, a non-vacuum fabrication leads to better efficiencies. In CIGS, vacuum-based route lead to better efficiencies, whereas in perovskite, both the routes can be used for getting highly efficient cells. Now coming to the properties of the three types of solar cells. So they all have a tunable band gap, that's not an issue. But for the best efficient cells, we see that in CIGS, the best part was getting higher short circuit current, because of which we are getting better efficiency in that case. Perovskite do have good open circuit voltage, but there in that case only the short circuit current is less compared to the other two technologies. So overall fill factor is best for CIGS among all the three. And here we see that the perovskite, only the thickness of the sensitizer layer is less compared to the other two technologies. And here we must compare the theoretical efficiency of the three technologies. Here we see that all of them are somewhere hovering around 30%. So theoretically the efficiencies can go up to 30%. However, practical efficiencies, as we see in the row below, that for CIGS only it has reached up to 21% lab scale efficiencies, and this is the only technology which has been commercialized till date. So commercial efficiencies are around 15%, whereas the other two perovskites have better efficiencies compared to CSTEP. So that is one of the directions in which the research is going on. So coming to the historical efficiency trends and the limits, so as I mentioned in the last slide, the dashed lines show the limits, the theoretical limits for efficiency, and the solid lines here show that historically since 2008 till date we have seen the increase in efficiency. These are actually the efficiency resistance lines basically. That is, of all the available literature, whatever information we got, we plotted that and then took the maximum over these years, whatever maximum efficiency was obtained since these from 2008 to 2014, and then we have shown these lines as to how much the efficiency has progressed over these years. Here we can clearly see that the black line perovskite shows a very steep increase in efficiency, whereas the yellow line CIJ shows that since 2008 its efficiency has not increased much. CSTEP on the other hand doesn't show a very steep increase, yet it shows a very good amount of increase in efficiency compared to CIGS. This is another plot showing the efficiency and fill factor comparison. So here clearly we see that CIGS lies in the top spot, because here CIGS has the maximum efficiency as well as fill factor among all the three technologies. And here that is the reason it has the highest position. Perovskite just come below it, followed by CSTEP. However, it's not improbable that perovskite will take over the highest position in a very near future, in a very short time. And we've also evaluated the material requirement from a particular technology, that is from either CIGS or CSTEP or perovskite. And for doing that, we followed this kind of algorithm. That is, suppose we say that certain percentage of the JMSM target, that is the National Solar Mission target, for domestic manufacturing is suppose 10 gigawatt, and a certain percentage of it has to come from any one of the technology, either CSTEP or CIGS or perovskite. By taking that, we calculate how much of power is needed. That is, suppose 10 gigawatt is the target. Suppose 30% of it has to come from either CSTEP, so it's 3 gigawatt. Now taking that much power requirement, and we know suppose we know the efficiency of the material, then we can calculate the area, that is divided by insulation and area, we get the area. And to know the thickness of the material, we calculate the volume. Taking the density of the material, we calculate the mass of the material in tons. And based on the stoichiometry, we calculate how much mass of the individual or the constituent element of that particular material we need. That is, for suppose for CSTEP, we'll calculate how much of copper is needed, zinc is needed, tin and sulfur is needed for obtaining this particular target of power. So based on that algorithm, we calculated for 20% or 30% target of the 10 gigawatt, how much material is required from CSTEP, CIGS and perovskite, based on the stoichiometry and efficiency mentioned. So here we clearly see that so copper, zinc, tin and sulfur requirements is not an issue, because all of them are abundantly available materials. But in CIGS, the amount of indium required for production might not be sufficient in future, because there is a problem of availability of indium in the future. For perovskite, it's basically carbon and hydrogen, nitrogen have not been shown in the chart because they are all actually occurring elements. Only lead and iodine have been shown. Here the toxicity of lead is an issue, but nevertheless abundance of lead is not an issue. So this much amount of lead is needed for making of perovskite. So coming to the conclusions, we can say that perovskite emerges as one of the potential candidates, because one of the reasons is that there has been a very steep increase in efficiency over the last 4 years, because of which there has been a tremendous increase in its efficiency and its other parameters, and there has been a very sharp improvisation in the technology as well. Yes, there are certain issues like the toxicity of lead is a concern. There are stability issues also involved with perovskite. But with more and more research in this direction, it is likely that this technology will take a huge turn. CSTEP is another one which can be pursued in future. However, if the efficiencies are coming to a comparable level with other symptoms. Otherwise, even though it has abundantly available materials, if the efficiencies fall much below the other symptoms, there is no reason for pursuing such a technology. CIGS currently, though it has very high efficiency, and that is the reason why many industries are pushing for this technology. However, in future, the limited reserves of indium and gallium can play a very big role in increasing the cost of this technology, because of which it might be a failure altogether. So, out of all the three technologies, in my opinion, perovskite is one in which a lot of focus should go into. Thank you.